Hello, I'm Richard Elgato, and today I'll be presenting my findings from the activity Orbits and the Moon. So starting off, we're given a chart of information on the Moon. First, we have the dates that the Moon was observed from September 1st all the way to October 1st, 2021. 12 p.m. was our time consistently. We have our ECL longitude in degrees. Then we have the lunar distance from Earth and Moon, or the lunar distance between the Earth and Moon in AU. And then we had a bunch of polar coordinates that we shifted over to Cartesian coordinates using the formula above. And this is the data that we get. And then on the right, we have the phases of the Moon for each given day. So if we plot the information here on a scatter plot, this is what we get. We get this perfect ellipse, or almost perfect ellipse. Give me a second. So, starting off our analysis, this blue dot is September 1st. It is the Moon on September 1st, 2021. The phase at that time is a waning crescent. This is our Earth, and it takes roughly 27 days for the Moon to hit a full orbit around Earth, which I will go through later. As discussed, the Moon completes one full orbit in 27 days, or 1/13 of a year. Which this is going to be our P, or period variable, for later. So this is I numbered each moon to its respective day. So 1, 2, 3, 4, all the way. So going all the way around, 27 days right here. The gap between the 28th and the 1st is way smaller compared to the 28th and 27th, or the 28th and the 2nd. So that's why it's 27 and a fraction, or 1/13 of a year, instead of 1/12 of a year, because it's in the middle somewhere, not directly in the middle, but it's a fraction or a decimal. And the phase at the end of the orbit is third quarter. This picture right here is specifically the September 28th, and the picture of the 29th is essentially the same thing. It's just it's less percentage of the moon highlighted. Pretty much still third quarter, but starting to ease its way into the waning crescent. So phase at the end of the orbit is a third quarter. So right now we're looking at the radial distance at perigee, variable RP, which is essentially when the Earth and Moon are closest, which is on September 9th at a distance of 0.002449 AU. Again, this is going to be our RP variable used when calculating eccentricity. Now we have the radial distance at apogee, variable RA, which is when the Earth and Moon are furthest apart, which is on September 25th, 2021, with a distance of 0.002708 AU. Again, this is going to be our RA variable, which will be used for eccentricity. And right now we're looking at the average distance between the Earth and the Moon, which is approximately 0.00258 AU. And this is going to be the Moon's semi-major axis, variable A, and we'll be using that at the very end of the presentation. So, eccentricity, what is it? The simplest way I can define eccentricity is the calculation of how much an ellipse strays away from being a circle. Essentially, an eccentricity of 0 is a circle, but an eccentricity of 1 is a parabola. So being in the middle of that, you get an ellipse. So where's my laser pointer? So here is basic criteria of what we need to meet and to know that we have the right eccentricity for our ellipse. So the eccentricity formula, I guess, explained or broken down. So the top of the formula is the distance between the foci, and the bottom is the length of major axis. So when we plug in our information, we got 0.002708 minus 0.002449. That'll equal 0.000259. And then for the bottom, you get 0.002708 plus 0.002449, and that equals 0.005057. So with that, we have 0.00259 over 0.005157, and that's going to equal 0.0502299, which I rounded it to 0.05. And if you plug it into our criteria, it matches perfectly. So as I'm pretty sure y'all noted, the phase at the beginning of the orbit and at the end of the orbit were different. The beginning was a waning crescent, while at the end it was a third quarter. Why is that? Well, the Earth's orbit around the sun adds distance, essentially, that the moon has to orbit. So the moon is always behind, essentially trying to keep up with Earth and its orbit with the sun. So officially, we know that the sidereal month, which is the time it takes to orbit the Earth once, is 27.3 days. And then our synodic month, which is the time it takes for the moon to go through its full phase cycle, is 29.5 days. So a difference of about 2 days, which adds up. So finally, we're discussing Kepler's law and whether it can be used to find the mass of the Earth. So Kepler's law states that the planet's period in years squared is proportional to its orbital size cubed, which period in years and then the orbital size in AU. So that this alone doesn't give you what you need to find the mass of the Earth. But after applying Newton's laws, you find that it is possible. Here's our variables right here of mass. So here we have period squared equals parentheses 4 pi squared over the gravitational constant times the addition of mass 1 and mass 2, close parentheses, multiply all that by the orbital size cubed. So continuing our discussion onto whether Kepler's law could find the mass of the Earth, here we have our basic Kepler's formula right here. We have the Kepler's formula with Newton's laws applied. So if we substitute for the variable that we want, which is mass, we would get that mass of Earth equals parentheses 4 pi squared over the gravitational constant, close parentheses, multiplied by the size of the orbit of the moon cubed over the period of the moon squared, and that will give us our mass, which after plugging everything in, this is what our formula would look like. So to answer the question, yes, Kepler's law with the influence of Newton's laws applied can solve the mass of the Earth. That concludes my presentation. Thanks for listening.